Welcome to Lecture 6.1, Symbolic Solutions for Linear Systems for Introduction to Programming and Mechanical Engineering. By the end of this lecture video, you will have an understanding of how to plot a linear system using symbolic equations, how to write a linear system of equations using the Symbolic Toolbox, how to solve that linear system using the Symbolic Toolbox, and how to access the solution values as double precision floats. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. We used the following example in the previous lecture. The linear system 2x plus y plus 3z equals 10, x plus y plus z equals 6, and x plus 3y plus 2z equals 13. And we had the following hand-drawn graph to illustrate the solution to the system. Let's now use the Symbolic Toolbox to replicate this plot in MATLAB. Note that the y-axis is oriented upwards in the previous graph, so we'll define our equations in the form y as a function of x and z. The first equation is y1 equals 10 minus 2x minus 3z. The second equation is y2 equals 6 minus x minus z. And the third equation is 13 minus x minus 2z, all divided by 3. These can be defined as symbolic variables y1 of x and z, y2 of x and z, and y3 of x and z. First, we define the equation in the rearranged form from the previous slide for the blue plane. Then we use the fsurf command to plot the symbolic function over the interval, which is described by umin, umax, vmin, and vmax. In this case, 0, 15, and 0, 15. At this point, the plot is shown here. Before we add the other planes, let's modify this plot window. We use the zlim function here to modify the z-axis limits. Note that the original plot only considered positive x, y, and z. The interval in the fsurf commands 0, 15, 0, 15 already sets the limits for the x and z directions. The zlim, 0 to 15, sets the limits of the z-axis in the plot, which is our y-axis. Again, remember that the y-axis in our plot is oriented along MATLAB's z-axis. Now the plot looks like this. Now let's adjust the camera's position to more closely match the original graph. The view command takes azimuth and elevation values as arguments to orient the camera around the plot box. Now the plot is oriented like this. Note that the x direction is backwards here. This command flips the direction of the x-axis so that 0 is on the left and 15 is on the right. Now we use the daspect command with equal ratios of 1, 1, 1. The daspect command scales each axis according to the ratio of the values in the argument array. We definitely want a uniform scaling for this example, and now the graph looks like this. Now we can add more planes to the figure. We start by adding the green plane. Note that the command hold on at the top is used to preserve the contents of the figure before adding the green function. Otherwise, it would overwrite the figure. Finally, we add the magenta plane. Now we already know the solution to the system from the last lecture, which is x equals 2, y equals 3, and z equals 1. We use the scatter3 command with those values as the first three arguments to plot a point in those coordinates. Note that because the y-axis is oriented on the z-axis in MATLAB's figures, those values are switched. The last three arguments in this command are used to specify the size of the circle as 20, the color to be red, and the circle to be filled in. Now the plot looks like this. Here, we just add some text labels to all three axes, and then we adjust the tick markers to match the original plot, where it marks out 0 and 3. Then, to get a more clean plot box, the commands grid off and box on turn off the grid lines and on the background box edges. And finally, we increase the font size of all text in the figure to make it more visually accessible. This is our final figure. Now the Symbolic Toolbox offers a solve command to automatically solve a system of equations. The equation's argument is a vector of symbolic equations, and the var's argument is a vector of symbolic variables within those equations. Let's illustrate this with a very simple equation example. First, we define the variable as a symbol using the syms command and the variable name x. Then the equation can be defined as follows. The equation is equal to 5 times x plus 7, which is equal to 12. Note here that the double equals sign is used for the equality within the equation itself. The single equal sign assigns the whole equation to the variable on the left. Now we can use the solve command to solve the equation. Thankfully, it is simple enough that we can also do the math ourselves, and we know that the answer should be x equals 1. This is the case as we see here. As you might imagine, you could use this to solve much more complicated individual equations for a specific variable, but you can also use it to solve multiple equations together. Let's return again to our original example with 3 equations. The first equation is written out symbolically by defining the variables x, y, and z, and then writing the equation just as it is read in the math. Equation 1 is set to 2 times x plus y plus 3 times z equals 10. The second equation is written the same way as the equation in math. Equation 2 is set to x plus y plus z equals 6. And the third equation is the same. Equation 3 equals x plus 3 times y plus 2 times z equals 13. Altogether, the entire system of equations is written here with the 3 symbolic variables defined, all 3 of the equations written out, and note that all 3 equations are now stored in a vector, and all 3 variables are also stored in their own vector. Then the system is solved as follows. Solution equals solve equations and variables, which produces the output that solution is a struct with fields x is 2, y is 3, and z is 1. This is exactly the same result that we saw in the previous lecture. Note that the solution variable is denoted here as a struct. In MATLAB, structure arrays are used to store different related information together. For example, a struct that describes this course might be defined as follows. Course.name equals Introduction to Programming and Mechanical Engineering. Course.department is equal to the text MEMS. And course.number is equal to the value 1140. The output of this struct in MATLAB is as follows. Course is a struct with fields named the text that we set, department is the text that we set, and the number is the value that we set. Dot notation is used to access specific elements of a struct in MATLAB. To access the name, write course.name, which returns the text that we set for it. Note that the return value is the entire character array itself. To access the department, write course.department, which returns the text that we set for that. Again, the character array itself is the return value. And finally, to access the course number, write course.number, which returns the value that we set for that, 1140. Again, the numeric value itself is what is returned. Let's return to the linear system from earlier. To access the values of each component, use dot notation with each variable. To access x, write solution.x, which returns 2. To access y, write solution.y, which returns 3. And to access z, write solution.z, which returns 1. These results are stored as symbols in MATLAB, not the normal double class. That means that if the values are not integers, they will be reported as fractions when the output is displayed. Here, the rational values are not simplified at all in the output. The double command can be used to convert its argument into the floating point format. I won't go into that format right now, but if you're interested, feel free to look at the documentation linked here. Passing solution.x into the double command returns 2.2. So in this example, the value of the symbol, which was 11/5, is converted into a double, which is 2.2. In summary, this lecture covered how to plot a linear system using symbolic equations. Each 3D equation is written as a symbolic equation f of u and v, and then plotted using the fsurf command over a given domain in u and v, written out as one array. Writing symbolic variables and then equations for a linear system of equations can be done just like they look in math. Note that the double equal sign is used for the equality within the equation itself, and the single equal sign is used to set that equation equal to a variable. All of those equation variables are then stored in an equations array, and the variables are stored in a separate vars array, and the solve command then uses those two arrays to automatically solve the system of equations. And finally, the return values from the solve command is a structure array. The elements of that structure array can be accessed using dot notation and then converted to double precision floats using the double command.